In this lecture, we'll see the parameterization of Markov random fields. So, the conditional independence properties of undirected graphical models are simpler and more natural compared to directed graphical models. But when we discuss them that is when we do parameterization, it's comparatively difficult because here we have to see that uh, we have to look it in terms of the potentials defined over the clicks. So the potentials are captured locally as a dependence between variables, but you can see that these potentials are not probabilities, so you cannot directly work with potentials alone. And by using only potentials, you may not be able to do inference also. So for doing inference, you may need to work with the joint distribution, the whole joint distribution of the potentials. So the joint distribution is defined as a proportional to the product of click potentials, and use that for doing inference. So this is the most famous theorem. Actually, the Hammersley-Clifford theorem says that the joint distribution of all the variables in an undirected graph is the product of potentials defined over a maximal click divided by the partition function 1 by z theta. So the joint distribution of all the variables in an undirected graph is the product of potentials defined over maximal click. So this is the set of all maximal clicks, potentials of all the maximal clicks, product divided by the partition function, and that is the probability distribution P of y given theta. So that is Hammersley-Clifford theorem. So here is an example of partitioning maximal clicks. So it is 1 by z theta into the click 1, 2, 3, then into click 2, 3, 4 into click 3, 3, 5. Right. So that is Hammersley-Clifford theorem. Undirected graphical models are very much related with statistical physics. This distribution, we write it in terms of energy associated with variables in a click. So here, each of these potentials e to the power minus e, where e is the energy associated with a click, using 1 by the number of nodes. So here we get the Gibbs distribution for energy of the system. So this is the potentials defined over each click. So potential defined over a click is same as the energy associated with the variables in a click. So maximum the energy means minimum its stability, right? So here the energy should be e to the power minus e, so the energy should be minimum, right? So next is pairwise Markov random field. Here, the parameterization is based on pairwise potentials. We can say that this is not about the maximal click here. The potential 1 2, then potential 1 3 2 3, etc. So this form is widely used because of its simplicity, but the representation based on the maximal click is more general. Here, what you're doing is you are using pairwise potentials. Next, we see how to represent these potential functions. Here is a very general way of parameterizing these potentials on the clicks, and this is what is called the log linear model. So the potentials you write here it as the log of the potential, log of its potential to be a set of some basis functions defined over the features yc. So we have a feature set yc. So these are the variable. These are the variables in the click. So with the dot product with a set of parameters. So this is the feature function phi c. Then the variables yc. Then theta c is the parameters. So this is a linear model, log linear model. In statistics, the log potential is expressed here as a linear model. Now, here is a general problem. The two tasks you need to perform is that what are these feature functions phi c? Then uh, these feature functions you can do it heuristically or you get it from the data itself. But the second problem is to calculate the parameter theta c. And that's where the concept of stochastic optimization will come into picture in a way that the parameters are computed. Remember, this is the log of its potentials over a maximal click, which is e to the power minus e to the power the linear term here. So if I take the log of this distribution, then this distribution is the product of all the potentials. So the log will give me the summation over. So log of the potentials means potentials are defined as the distribution is defined as the product of potentials. So you take the log of that, then you will get summation, right? So here this was a distribution, you take the log, then it will become summation. And so if I take log of this distribution, log py theta, then this distribution is the product of all the potentials, which will be summation of all these feature functions. So phi c yc phi c into theta c minus this normalization factor, and all these parameters are coupled through this normalization factor. And for example, let's say when we try to do maximum likelihood estimation or MAP estimation, we are going to maximize this term, right? So it will require integration over yc, and that will be a very difficult term to compute. So the resulting log probability is expressed like this: log py theta is the summation over this minus the normalization factor. As an example, if you work with the pairwise Markov field, Let's say here each of these random variables can take k values. So each of these feature vector will be an indicator function. An indicator function I, where y is equal to j and yt equal to k, which will be an indicator function which takes the value 1 if the variable has the variable y s is equal to j and yt equal to k. Uh, so here you are going to have a feature vector of k square values. So the potential within the table is effectively the same as the potential with the parameter theta st. There is a similarity between the discrete model and the log linear model, but obviously the log linear model is very general. In this case, pairwise potential, pairwise representation is a tabular form, and the other one is a linear model. Here is an example of English spelling. If you look at a document, and if you create a probabilistic model of English spelling, it could be an indicator function over three words. That is, T is the index. Here can see that T is the index. Those for three words, T minus 1, T and T plus 1. So you look at triples here. Theta k is the corresponding parameter. Theta k is binary functions that can take value 0 or 1. So this way you can identify certain words. For example, this is uh, so this is only for triples. So like words like ing, something similar, etc., can be found. The only problem here is that if you try to do this for a real text, then if you take some 26 letters of an alphabet, then it would result you in 26 raised to theta, which would be computationally very difficult thing to do, right?